So we're now recording. So everybody, because we have the best Congress money can buy, we've got this FERPA legislation which says you've got to be silent and invisible and anonymous. But the chat screen is open, and the pen names that you've chosen are quite amusing, and I think they add to the class. Well, we ought to start. It's now time. The topic that we started, I think, just briefly last time was dispersion relations, but I think to whatever extent we did it last time, it was very, very brief. So the idea is that you have, you imagine that you have a situation where you have a cause and an effect and a transfer function f hat. And f hat then would be a function of t and t prime, and where I'm assuming that it's a function just of t minus t prime. And then one would imagine that the transfer function would be 0 when t is earlier than t prime, because the cause is supposed to occur before the effect. So that means that this function f hat of t is 0 for negative t. And so in this Fourier transform, t is always positive. So we can put z into the upper half plane of the z-axis, and in that case, f of z will get smaller and smaller as we move z into the upper half plane. And that's what I pictured over here, where I added a ghost contour. Imagine a ghost contour around z0. So now we're dropping this these two equations, and we're just imagining that we have a function f of z that's analytic on the upper half plane, in the upper half plane, and on the real axis. And I'll add just, well, that it goes to a constant, let us say, as r goes to infinity. We don't really need, well, it goes to a constant for y equal to 0, it goes to a constant as r goes to plus or minus infinity. But as, so let's assume that at first. And so the ghost contour that I'm drawing that goes counterclockwise around z0 is one that starts at some huge positive value, little r, which I probably should have written as big R, capital R. Anyway, it then rises in the complex plane at distance c. And then when it's sufficiently high in the c complex plane that this number, that this modulus is very small, and it's very small because we're imagining that that f satisfies a condition like this, which would be a consequence of its being the Fourier transform of a function that has that vanishes when the other variable t is negative. So in that case, the integral along c at either a large positive or a large negative value of z will be bounded by that large value of r, or equivalently of z, and it's just then the numerator is just the absolute value of f, and we assume that that goes to a constant as we go out to infinity, and so this ratio goes to 0. So these two parts of the contour are certainly ghost contours. And then when we go around this, the North Pole, we take advantage of the fact that we imagine that this goes to 0 exponentially with, as the imaginary part of y increases. One can essentially use this, this criterion here. But as I said, this criterion works if we just do a simple great circle that does this. Whoops. In other words, a circle that goes like that. But if instead we just assume that at large positive and negative values it goes to a constant, then we get away with these parts. See, the issue here is that the imaginary part of y is not large in this part of the contour. And that's why I did a straight line, which kept us at very large values of r. Or one could just say that this is bounded on the perimeter. There are various conditions that one can add, and the upshot is that this is a ghost contour and it's equal to 0. So what we're done with then at that point is that f of z0 is by Cauchy's integral form. It's 1 over 2 pi I. An integral along the real axis of f of x dx over z becomes simply x. And so we get x minus z0. And now we're going to shrink the imaginary part of z to z0 to epsilon. And so we have this expression here. Now we use Cauchy's trick. And let me flip back to Cauchy's trick here, which is 1 over x minus y plus or minus I epsilon is the principal part of 1 over x minus x minus y minus a plus I pi delta of x minus y. And damn, this thing keeps coming in the way. And so now if we go back here, what we do is we see that this thing then is the principal part, and there's a minus sign here, so it's plus I pi times the delta function, and we keep the 1 over 2 pi i's. And so that's the expression that we have. This integral is very easy. It's just a half f of x0. And so we subtract it from both sides, and that means that f of x0 is 1 over pi I, a principal part of this integral. So that's the general dispersion relation. Now, if we break f into real and imaginary parts, we have on the left-hand side u of x0 plus iv of x0, and on the right-hand side u of x plus iv of x. And then we can separate this into a real part, the u and the principal part, and then an imaginary part, which is a somewhat different principal part. Notice that the real part of the right-hand side uses the imaginary part of the function f, and on the other hand, the imaginary part of the right-hand side uses the real part of the function f. And now that's a complex equation. It breaks up into two real equations, one for the real part and one for the imaginary part. These are called Hilbert transforms. Hilbert was a mathematician around the time when Einstein was alive. And he also contributed to mathematical physics and suggested using the Riemann scalar. Let me go back to black. Riemann scalar R as the action for gravity. Here G is the absolute value of the determinant of the metric. Whether he stole that formula from Einstein or invented himself, I don't know. I've heard both. Anyway, it's clear that Einstein was a great physicist of that era. No question about that. Now, obviously, when we look at these two equations, or this equation, we see that X is some physical variable. The dispersion relations are incredibly general, so it could be any physical variable. But it's often true that the physical variable is experimentally accessible only for positive values of the variable. And in that case, the function f of x for negative x can either be meaningless or experimentally inaccessible. However, sometimes f of x is the Fourier transform of a real function, in which case it obeys the Fourier transform identity that the complex conjugate of the Fourier transform of a real function is the Fourier transform evaluated at minus the argument. And so we get this complex equation. And this tells us, looking at identifying the real parts, it tells us that the function u, which is the real part of f, is even, and the imaginary part of f is odd. And in that case, we can simplify these equations. This one being even, it means that we can just integrate over the right-hand side and multiply by 2. And then over here, because v is odd, what happens is when we absorb the left-hand side, we get something like 1 over minus x 0. And then when we add the two together, we get this expression here. This is one of the exercises, actually. All right, this is a good time to pause if there's a question that somebody wants to shoot to me on chat. Although questions are always on chat are always welcome. Well, anyway, let me go to the Kramers-Kronig relation, which are important in electrodynamics and quantum mechanics. As you know, people often like to avoid using sines and cosines because the sines and, here. Okay, what's the question? So the question, I guess everybody can see the question, so I'll just try to answer it. In this particular case, the reason why I did this is that if all we know about f is that it's the Fourier transform of a function that vanishes on the negative real axis, then we just know that, let me switch to blue here. Then what we know is that f of x plus I, y in absolute value goes to 0 as y goes to infinity. But now, if we do a contour that's a circular contour like this, then in this part of the contour, y is not huge. The thing that's huge is x, because x is the distance from the origin here to the point there. So that's why I chose to integrate up here and then down there at values of huge x. I don't know, maybe, I mean, I'm sure you can argue that because even though y is small here, nonetheless, the 1 over r is going to be huge, and x is not going to shrink very much as we go along the circle. So I don't know, one could work that out. I just thought it was easier to think in these terms to keep x huge by going vertically up. And then when we get to a value of y that's small, that's large, we can rely on the smallness of f as y grows. In other words, this relation here. You know, the deal is with ghost contours, if you add a ghost contour, you have to make sure that it is a ghost contour. And sometimes that's easier for a square contour, as when we were doing the Fourier transform of a Gaussian, the very first time we did that by completing the square. I used a contour that wasn't fully a ghost contour, but I used a contour that was like this, remember? And so I said the integral along this is actually 0, and the reason I did that was that, here, let me get, now I can't get the colors, oh, here we are. So I wanted to, I was able to show that these two line integrals are super small. It was super small in that case because they were like e to the minus x squared. And then the result is that the integral along this contour is equal and opposite to the integral along that contour. And that allowed us to show you that you could add an imaginary part to the independent variable when completing the square in a Gaussian. Okay, I hope that's the right answer, but anyway, it's whatever is convenient. You know, you choose the ghost contour so that you're certain that the integral along the ghost contour vanishes, and you choose it so that it's useful to you and the easiest one to show that, and that it's easy to show that it vanishes. Anyway, to get back to Kramers and Kronig, people doing electrodynamics often use complex variables so as not to have to screw around with sines and cosines all the time. And so they would let E be, if they know that it's something going, that the frequency omega is crucial, then E is e to the minus I omega t times some real E. And then B is given by the curl of B equal to the current plus the time derivative of E. And then we get this expression here. And if we baptize n squared as being this, we can then get this equation here. Now this, the nice thing about this expression is that it tells us that n squared of omega, well, it goes to 1 at large frequencies, at high frequencies. And so then what you can do is you can apply the Hilbert Transforms relation not to n squared, but to n squared minus 1, because then n squared minus 1 goes down as 1 over omega. And you can argue then that your ghost contour vanishes. At this point, the Hilbert transform relations take this form. And I think I'll go through just a little bit of this. What Kramers and Kronig actually did was they used a result by Lorentz, which was that the index of refraction is 1 plus the forward scattering amplitude, for the scattering amplitude of light off the atoms of a substance or molecules of a substance, density n, and it's 1 over omega squared. And so then, if that's the case, again, n approaches 1, but really fast. They then wrote down these equations, which again are Hilbert transform relations. and so the real part is related to the imaginary part of n. So that's essentially this equation. Just that here I wrote omega and here I wrote omega prime. I probably should have kept the same notation. Anyhow, they then wrote the imaginary part of n in terms of the imaginary part of f using this expression here. And then they used one of the magical results of quantum mechanics, which is the optical theorem, which is extremely general, by the way. It applies also in high energy scattering theory. And it says basically that the total cross section is proportional to the imaginary part of the forward scattering amplitude, forward elastic scattering amplitude. And here we have photons being scattered by molecules, and we're thinking of the elastic scattering amplitude. Anyway, what we have is then that the imaginary part of n is related to the total cross section divided by the frequency, and so then the real part is using this equation here. The real part is then related to the real part of f, like that. And so then we can say that the real part of the scattering amplitude, the forward scattering amplitude, is an integral involving the total cross section from 0 to infinity. This again is one of the Hilbert Transform relations. And so that's, I think that, let's see, what does the imaginary, well, what the imaginary part of the index of refraction means is that when you put n, it's actually the imaginary part of the square of the index of refraction. At least there it is. Oh, here though it is just the index of refraction. Well, if it's whichever it is, whether it's n or n squared, the imaginary parts are of course related. And then once you get n squared and you put it into this classical equation, one of Maxwell's equations, you have then a complex equation for the way the magnetic and electric, way the magnetic field responds to a given electric field. And you can then solve this as a complex equation. And then you take the real part and you find out what the magnetic field is due to this electric field. So it's basic, and it's also that the imaginary part is due to the scattering of light by electrons, mainly by electrons. Protons also scatter light, but the protons, because they're 2,000 times heavier, do much less scattering. Okay, now let's switch to phase and group velocities. This is important classically and quantum mechanically, or it's important in classical physics and in quantum mechanics. The idea is that we we use a Fourier transform relation that's often true of anything that satisfies the wave equation. So here the idea is that, you see, since, let me maybe switch colors here to black for a moment. So basically, if we're saying that a of x and t is an integral e to the I p dot x minus et, and then if we're using universal units, we divide by h bar, and then we have a of p dqp. This is a solution of the wave equation in the sense that partial 2 partial t squared minus the divergence of the gradient acting on A, well, what will that be? Well, the d by dt squared is going to pull down a minus e squared over h bar squared. And then we're going to have minus grad, and the minus signs cancel. So we get plus p vector squared over h bar squared. And I just wonder whether my units are not quite right. And we also want to add in a plus m squared. So that's the mass of the field. So we have plus m squared times a of p dqp times this phase factor cos e to the I p dot x minus et over h bar, and there's an I there. And so so we get 0 as long as I've got the right units for m squared. I usually work in what are called natural units. In other words, units with h bar and c equal to 1, because then I can just don't have to write so many h bars and c's and so forth. So this is, you get 0 there if e squared is equal to p squared plus m squared. And I now see that I probably have left out a factor of c in this equation here, because the actual equation is that this is m squared c to the 4th, and it's c squared p squared plus m squared c to the 4th. So I should have had an extra c, so there should have been a c here. So if I bring in some red here, well, here, let's just, there. If I do that, then what I'd want here is a c, and then once I've got, so that then would bring, that would be c squared p squared. And then what about m squared? Well, that m squared should be m squared over h bar squared. That may be it, and maybe it's just m squared over h bar squared. Anyhow, if one, I don't think I should dwell on that any longer. The main point here is that that the way this function evolves depends upon, or you can approximate how it, you can characterize its evolution in time in terms of phase velocities and group velocities. And of course, if we switch from these physical units, universal units, to something closer to natural units, we have this expression, and so what's the phase velocity? The phase velocity is the linear relation between x, between position and time, such that we keep the phase constant as a function of the time. So that means that we rewrite this sum of two differentials as dt times p dot something else, v phase. And that means v phase is e over p times p hat, or omega over k, k hat. So that's the phase velocity. And what you find is, for light in the vacuum, the phase velocity is just the speed of light, which is omega over k. For a particle of mass m greater than 0, then the phase velocity, in fact, is higher than the speed of light, and so the phase velocity can't mean a great deal physically. What's more physical is the group velocity, and the group velocity is the linear relation between x and t that maximizes the amplitude a of x and t by keeping the phase constant as a function of the momentum. And it's the function of the moment because we're integrating over momentum. This should be constant as we integrate over momentum, not as we change the time. The time is irrelevant here. We're doing an integral over momentum. And so we say then that the gradient with respect to momentum of p dot x minus et should vanish. And of course, that gives us x minus grad p of e of p times t. And then that gives us a stationary phase relation that Vg is just the gradient of the energy, or the k gradient, momentum gradient of the energy, or the k gradient of the frequency. Now, non-relativistically, E is p squared over 2m, so the group velocity is then the p gradient of this, and that's just the momentum divided by the mass, which of course is what you normally mean by the physical velocity. And for a relativistic particle, we get this expression. It's always less than or equal to the speed of light, and if the mass is non-zero, then it's strictly less than the speed of light. I think I'm going to skip the rest of this. Those of you in optics will ought to read it. And if somebody's curious about this, I'm willing to do this as part of the 468 lecture tomorrow afternoon. Let's now go, though, to something called the method of steepest descent, which is a way of approximating integrals, and this will allow us in particular to derive Stirling's formula for n factorial. So let me first of all switch colors for a little while, and let me show. Well, let's first consider the integral that is sort of a general case of an integral. So it's this equation 6326, and this is e to the r times f of z. Okay, now, as Biden would say, here's the deal. What we're imagining is that the function f is analytic here, and h is also analytic, and we're in a simply connected region, and so we've got some region here of analyticity. We've got an A over here, B there, and so we can choose any contour we want, and whichever one we choose, including crazy ones that do this, the contour integral, all three of those contour integrals will be exactly the same. So the idea is to choose a contour integral that allows us to approximate this integral. And the important thing here is that this integral is sensitive to the, let me switch colors again. So let me switch maybe to green. So this is the part that, I mean, I'm assuming here that h is a relatively simple, calm function that doesn't change very much, or at least doesn't change exponentially. On the other hand, this other function obviously changes exponentially, and it is equal to then e to the r times u of z plus I v of z. But R, we're thinking of R as real. That's why I use the symbol R. So this is very sensitive to U of Z. It doesn't care quite so much for V, but it's really sensitive to U. On the other hand, if V varies rapidly, then it's also sensitive to V. What do we do? Well, the idea here is that we look for, well, what we know is that U and V have saddle points, but no minima, no local minima or maxima. So what do we do? Well, so what that means then is that this R U of Z plus I V of Z, these functions U and V can get very big or very small, but we can't find a local minimum or maximum for that matter. And so what we do is we imagine that we've got, let's suppose I switch colors again here. Let's go to maybe red again. So the idea is that if we have A over here and B over there, we choose the integral so that it goes over goes through a saddle point where f of z has no derivative. So this is u prime of z plus I v prime of z. In other words, it's or if we switch to x and y, we can say that well, f prime equals 0 is equivalent to u sub x equals u sub y equals 0. And that tells us by the Cauchy-Riemann equation, we also have v of x equals v of y equals 0. So we want this because we're going through a saddle point of u. And at that point we have f prime equal to 0, so we can say that f of z is f of w plus a half z minus w squared f double prime of w. So that's what the function is there, and that's this equation here. So the next thing is to, now w we're going to keep fixed, so w is fixed at saddle point. And f double prime of w, of second derivative of f at w, is then some complex number rho e to the I phi. And now we choose our contour through w. And what I should have done was maybe change colors a little bit here so as to indicate what this looks like. In other words, this thing is going up here. And we're going over a pass here. So it's like what people who make railroads or just ordinary roads do. They choose a path for your highway or your railroad that goes through a saddle point. Well, the deal is that you see RU changes the magnitude, whereas V changes just the phase. So, so what you want is, in fact, what we're going to do is we're going to integrate along a straight line in which, you see, in which we're going to arrange that f of z is f of w, and then it's going to be a Gaussian around that, so it's going to be decreasing. So what we do here then is we choose our contour. Z is going to be the fixed saddle point plus some real number times a phase, and we're going to keep that phase constant so that we, as we zip through this saddle point, and keeping theta fixed for Z near W, and of course W is fixed. Now, so near there, F is F of W, which is fixed, and then this quadratic term. And what we want is that that quadratic term, which of course F double prime is rho e to the I phi, if Z is Z minus W is S e to the I theta, then this is S squared e to the 2I theta. We want to keep this negative so that we're basically, so that we've got this thing that's effectively a Gaussian here. And then on the other side, it's another Gaussian. And so to do that, we set 2 theta plus phi equal to pi. So near the saddle point, f of z is f of w minus a half rho s squared. And so then dz is e to the I theta ds. That's from this equation. And the integral then has this complicated exponential here. We're saying that h, again, is compared to the exponential, it's completely asleep. So this is a sleepy function. And f of w, well, f of w is, what did we say? Well, f double prime of w is that. Right, the function though is we have e to the r f of w, and we just, that's a constant, so we pull that out, e to the r f of w, and the dz has an e to the I theta in it, so we pull that out. So what's left is a ds e to the minus a half r rho s squared, because this is what was left, the rho s squared, the phases we pulled out, and r is this real number that was right here. Okay, so we've arranged then for this to be negative, and so then we just have this Gaussian, and we know what the Gaussian integral is. It's in this case, it's square root of 2 pi over r rho, and then we have the constant factors in front. So what I like to do is to take this phase factor and move it inside the square root, leave h outside, leave this outside, and now we know that f double prime is rho e to the I theta, rho e to the I phi, and we know we fixed 2 theta plus phi equal to pi. So we can say that this e to the minus 2I theta, or rho e to the minus 2I theta, is rho e to the I phi minus I pi. The minus I pi just gives us a minus sign, so we have rho e to the I phi, but rho e to the I phi is what f w double prime of w, what f double prime is at z equal to w. And so in fact, this approximation of the integral is the h factor, the e to the r f of w, and then the square root is square root of 2 pi over minus r f double prime of w. So that's a nice compact, exact expression for the case where h is slowly varying and r is a real number. So the question here was, why did we write the second derivative of f that way? Well, the second derivative is something. It's bound to be, it's a complex number, so it has a real part and a phase. So this is the modulus of r. The absolute value of f double prime is rho, and the phase is phi. So it's so we can always write it f double prime like that. So let's, you're welcome. Let's derive Stirling's formula. And first of all, we know that there's an exact formula for exact expression for Stirling's formula. Namely, it's minus 1 to the n, the nth derivative of y inverse evaluated at y equal to 1. So that's kind of that's not the most obvious expression, but if you start differentiating, you can see that that actually works. Maybe I should, here, let's switch colors again. Let's go to black, maybe. So first of all, minus 1 dy inverse dy is equal to minus 1 again, y to the minus 2 evaluated at y equal to 1. So this is just equal to 1. But now if we differentiate yet another time, we're going to get minus 2 minus 2 y to the minus 3 evaluated at y equal to 1. So this gives us minus 2, but there's an extra minus sign because it's minus 1 to the n. So this actually goes to plus 2, which is equal to 2 factorial. So then if you do it a third time, you're going to bring down a 3, and the 3 multiplies the 2 and so forth. So this is an exact expression. But now we can differentiate inside, and that brings down z to the n. So now we have a very, and we've integrated here along the real axis from 0 to infinity. So this is integral 0 to infinity z to the n e minus z dz. Now we rewrite that in the form, in this form, and h we can let equal to 1. We write it in this form, and it's e to the n, z to the n is e to the n log z. And then we have the minus z. And so comparing it to this integral, what we see is that f of z is n log z minus z, and we set r equal to h equal to 1. The saddle point is where f prime vanishes. Well, if you differentiate with respect to z, you get n over z minus 1 equals 0. So z is equal to n, and is where it vanishes. And so we set w equal to n. And moreover, if we can then compute the second derivative at z equal to n, we just get minus 1 over n. So if we now go to our, we just plug in the formula for the plug-in being this. What we do is we pull out the e to the n log n minus n, which is which is e to the r f of w, but r is 1, so it's just e to the f of w, and f of w is just, since w is n, it's n log n minus n. So that comes out. Then we have this Gaussian integral. The Gaussian integral gives us a factor that that altogether converts this to square root 2 pi n. So this e to the n log n is n to the n. So that's the n to the n term. E to the minus n is that term. And so the Gaussian just gives us square root of 2 pi n. So that's basically, that's how one derives Stirling's formula, which, as I said, is remarkably accurate for large values of n. And now, why is it remarkably accurate for large values of n? Well, we need large values of n so that we have a saddle point that is such that we can ignore everything except the saddle point and the Gaussian over the saddle point. Of course, if you have more than one saddle point, you have to split the integral into a contour that goes over each of the n saddle points. I think we can skip the string theory example, but if somebody is passionate about that, I can do it on Wednesday. So now we're into differential equations, and let me just repeat something that I said about complex variable theory. It all follows almost directly like dominoes, just a chain of dominoes, from the definition of an analytic function. So everything follows, all the results of complex variable theory follow from that. For differential equations, I suppose there are two really key things to say that apply very generally. The one is that any way that you find to solve any differential equation, is just fine. It'll give you a correct solution. If you found a solution, okay, you don't need to take it to some committee to get it approved. Any solution is a good solution. The other thing is that these differential equations are kind of two or three types. The first type is that they're linear and they have constant coefficients, and we can solve them just by the Green's functions techniques that we learned in the chapter on Fourier transforms and Fourier series. The next case is that they're linear differential equations, and then you can solve them by hook or by crook. But you can't just do them trivially with a Green's function, but one way or another you can do them. The third category is that they're nonlinear differential equations, and they are in general hopeless, and you have to use numerical methods. Now, of course, we're in an age of powerful and cheap computers, so you can basically solve any. You can do essentially anything. If you have a finite number of variables, you can do anything with modern computers. All right, so with that out of the way, let me just write down a general nth order ordinary linear differential equation, linear differential operator. So it's a sum of a bunch of derivatives. We're here with one variable. Ordinary means that the derivatives all are with respect to one independent variable x, nth order because the highest derivative is the nth derivative. Linear because derivatives are linear, and so the equation is the differential equation in this particular case is, let us say, L f of x equals equals 0. Let me show you two cases, or equals s of x. This would be a source function, and we'd say that the differential equation is inhomogeneous, and this would be a case where the source function vanishes, and then the differential equation, we would say, would be homogeneous. So I've lost track of what I was going to say, but anyway, when we call it an ordinary differential operator, we're not meaning that it's somehow trivial. No, it's just that it doesn't involve partial derivatives. All the derivatives are with respect to the same independent variable x. And it's linear because derivatives are linear operators. And so basically L A1 F1 plus A2 F2 is A L F1 plus A2 L F2. So, which is what is written here. So this is why it's linear. And if these h's are constant, then you're home free because you can use these Green's function techniques and solve the thing very, very simply. You just have, if L is equal to a sum Cn dm dx to the m, then you can just write f of x as an integral dk e to the I kx, and you can then say, well, you can make a Green's function, and for one thing, if you just want to solve the homogeneous case, then what you would say is that LF, well, this would be an integral dk, a sum Cn, but the mth derivative with respect to x would be Ik. Oh, here I have n and there I have m, so I was doing m. Let's do m up to n, and this is an m. And e to the I kx. And so, so you see the function, if we want this to be 0, then the function f of x is something that can be written, let's see, let me write it. And I'm writing this as delta so we have an arbitrary function h of k, e to the I kx, and then I put in a delta function. So when L hits F, what we get is integral dk sum Cm ups, let me just, sum Ik to the m, delta of sum Cm Ik to the m, e to the I kx h of k. And so this is going to be 0, because no matter what h is, this function is 0 whenever the argument of the delta function is 0. And so this thing just gives us zero. And so this is a solution of the homogeneous equation. So it's what I said to you earlier in the earlier chapter. If instead we want to solve the equation L f of x equals S of x, then what we do is we write both of these as Fourier transforms, and then we have the equation dk sum Cm I k to the m f tilde of k e to the I kx equals integral dk e to the I kx s tilde of k. And if we want these two things to be equal, well, then it's pretty clear that f tilde of k has to be s tilde of k divided by this sum Cm I k to the m. Now, I've been a little bit casual here with the argument of the delta function being having complex numbers there in it. The way we interpreted this in the section on Fourier and Laplace transforms was that we would integrate over the real axis, and we just have a Fourier transform, or we'd have to have k go up the imaginary axis and so forth. And so one would presumably have to do something like that in this case. So I don't know, maybe I shouldn't have done all of that analysis extemporaneously. But in practice, what happens is that the differential operator is such that this denominator here will either be real, typically it's either real or it's imaginary. And then we go either to a Fourier transform, or if it's imaginary to a Laplace transform. So that's, but as I said, I did that sort of spontaneously, and I think maybe I shouldn't do so much spontaneously. In any event, let's go back to an example of a second order ordinary linear differential operator is this, and this is the thing that occurs all over the place in mechanics and electrodynamics and physics and so forth, or quantum mechanics. An analogous or a more general second order linear differential operator is of this form, where P and Q are real functions. This is said to be in self-adjoint form, and we'll learn later that that's a nice form, and it's nice when you've rewritten your equation in that form. A differential equation is homogeneous if all the terms are linear in F, and in particular, that means that you have over here you have so all the terms are linear in F, so they have different derivatives of F, and the right-hand side is zero. You don't have some source term, so that's homogeneous. If you have a source term, then it's inhomogeneous. So let's look at the linear homogeneous case for a moment. And we see that because it's linear and homogeneous, if you have two solutions, you can add them, and that's so L of F1 is F1 is a solution, so L of F1 vanishes. F2 is a solution, L of F2 vanishes. So you can add them together, and you find, if you said F equal to A1 F1 plus A2 F2, L on F is L on this, but L is linear, so you have A1 L F1 plus A2 L F2. Both of these are zero, so you're home free, it's all zero. Sines and cosines, of course, are solutions of the this differential equation. And so the most general solution is a linear combination. You can add, this is a solution, that's a solution, so you can add them together. And this, of course, is what one does. What's less, what I don't like about this solution is that you then have to deal with sines and cosines, and they behave slightly differently under differentiation and integration. And so I find it easier to write this as e to the I kx for some k, and then we're dealing with a complex solution. Now, we talked about linear independence and linear dependence for vectors back in chapter 1. We can apply the same idea to functions, and we'd say that n functions, y1 of x, y2 of x, yn of x, they're linearly independent if the only numbers for which this combination vanishes for all x is to set all the k's equal to 0. So obviously, you've set all the k's equal to 0, you just have 0 equals 0. But if that's the only way that that a linear combination of the y's vanishes for all x, then we say they're linearly independent. On the other hand, if you can find k's such that this works for all x and the k's aren't all identically 0, then they're linearly dependent. So let's suppose for the moment here, we have an nth order linear homogeneous ordinary differential equation, L f of x equal to 0, and we have n linearly independent solutions fj of x, and that all the other solutions are combinations, linear combinations of these n solutions. So these n solutions that are complete in the space of solutions of the equation, when they form a basis, then you can think of them as vectors. And in fact, this, because the idea of a vector is extremely general. You can think of each of these functions as vectors. Anyhow, so the most general solution of this is then a linear combination of these linearly independent solutions. And on the other hand, if we have the same differential equation, but now with a source term, and Fi1 and Fi2 are any two solutions of this inhomogeneous equation, then the difference of the two will be a solution of the homogeneous equation, because L of the difference is the difference of the L's on the functions, and that's S minus S, that's 0. So that means that the difference of any two solutions of the inhomogeneous equation is the sum of all the solutions, all the linearly independent solutions of the homogeneous equation. Putting the F on the other side, we see that the most general solution, remember this one is arbitrary, so this is the most general solution of the inhomogeneous equation, the inhomogeneous equation being this one, is any old solution, any particular solution, and particular just means any old, John's or Mary's or Harry's, doesn't matter, your favorite solution of the inhomogeneous equation, plus the general solution of the homogeneous equation. So this is why we're all, even if we are dealing with inhomogeneous differential equations, we're always interested in the homogeneous equation, because the general solution of a linear inhomogeneous equation is any particular solution of that inhomogeneous equation plus the general solution of the associated homogeneous equation. Okay, that was just a note to myself. So far we've been talking about linear differential equations. And I said by comparison, they're trivial compared to the nonlinear differential equation. Nonlinear differential equations are one in which a power of the unknown function, or if one of the derivatives occurs. And a power, I mean quadratic, a square root, cube, whatever, or a function, a non-trivial function of the unknown equation. And so in other words, in this case, f prime is e to the minus f, or f double prime is f cubed, or f prime squared is f. These are nonlinear differential equations, and these are hard to solve. In general, you just have to be either a genius or you use a computer and do it numerically. But there are no general methods. They're all, everyone is sui generis. In other words, it's its own particular kind, and you need your own theory to do, to solve it. That, by the way, if any of you have read Feynman's introductory physics books, which of course are marvelous, but if you read them, what you find is that each time he considers a new example, he invents a new physics that's ideally suited to that example. And so, so the book is actually, because Feynman is so smart, the book is harder to read because he's smart, so very, very smart. It would be much easier to read a book in which you had, in the beginning of each chapter, you had one formulation of physics and then a bunch of examples that were all solved with the same formulation of physics. But instead, Feynman reinvents physics on the fly appropriately to solve each example. And so it's a workout reading his book. So partial differential equation. Well, a partial differential equation is, it's a whole differential equation, but it's a whole differential equation in which derivatives are, in which partial derivatives occur. And of course, a partial derivative is a whole derivative, but it's a derivative. So you have a function of n variables, or a function of more than one variable, and you hold all the variables except one fixed and differentiate with respect to the one that you don't, with respect to the one you vary. So, of course, you know all that. So here's a general nth order linear, partial differential equation in k variables. The solutions, linear combinations of a linear homogeneous partial differential equation are also solutions, because if L of F1 is 0 and L of F2 is 0, then A1 F1 plus A2 F2 is also sent to 0 by L, because L on that is A1 L of F1 plus A2 L of F2, and that's 0. So additivity of solutions to property of all linear homogeneous partial differential equations, or differential equations, whether ordinary or partial. And the general solution then of a linear homogeneous partial differential equation is the sum of a complete set of solutions. And these are, you choose typically a linearly independent complete set of solutions. And then if you have an inhomogeneous term like that, well, you know that if you have any two solutions of, in other words, Li1 and Li2, I meaning inhomogeneous, so Li1 is S and Li2 is also S, then L on the difference is 0. So the difference can be expanded in terms of the solutions of the homogeneous equation. And that means that an arbitrary solution of the inhomogeneous equation is any old solution of the inhomogeneous equation plus a general solution of the homogeneous equation. Well, we're just about out of time. There's 1 minute left. If somebody has a question. By the way, I should publicly maybe thank Mr. Birdwell for rescuing me at the end of the colloquium. I had a feedback problem, which between my iMac and my iPad, and he pointed out that that was the problem. It was during Zoom. Anyway, is there a question? All right, we really are out of time. So this virus, as I was saying, is really very dangerous. And we have now in, I don't know, what is it, 9 months, lost almost as many Americans in 9 months as we lost in World War II in 3.5 years of combat in North Africa, Europe, and the Pacific. And so this is a very serious situation. The fact that you don't hear any explosions, you don't see any blood, you don't see people shot to death, it doesn't mean that you're safe. We are all, it's as if we were all in a combat situation that's 3 or 4 times more deadly than the Second World War, than being a foot soldier in the Second World War or a Navy man in the woman in the Pacific. So it's extremely dangerous. Stay out of bars and wear masks and so forth. Okay, well, I'll try to put this on YouTube, and oh, that's strange. I don't see. I hope you guys are able to see the screen still, because I don't see the little border anymore. All right, anyway, I'm going to stop it because we're out of time. So I'm going to end the meeting. Goodbye, everybody. Stay safe.
Have a good night. Thank you.
Thank you.